Okay, here we have a video on connected particles. So this is a year 12 connected particles video, which means everything is going to act all in the same direction. So there's going to be no angles or anything. Okay, so what is a connected particle? Well, a connected particle is really what it says in the title. It is a particle of some form or another connected to another particle, each with their own mass, so perhaps M1, M2. And they are connected by something which contains some kind of tension force. Okay, label it T. And perhaps there'll be some kind of driving force on the system. There'll be some kind of resistance perhaps on the second mass and some kind of resistance on the first mass. And the job is essentially to consider, well, what's the acceleration of the system? Okay, and what's the tension of the insides there? Typically, you'll be given two unknowns out of the situation, and you'll need to resolve for the others. Resolve those from the known values. They're fairly straightforward. When you're looking for the tension, you have to either look at one of the masses, or if you're not looking for the tension, you can just treat the whole thing as one item. Okay, tension is what we would refer to as an internal force in the system. Okay, the tension acting on the second mass is equal in size to the tension acting on the first mass. And that's by one of Newton's laws, okay? Equal and opposite. All right, so it's essentially just that. Okay, and applying F equals ma and maybe even some suvat around those situations. So let's have a look at an example. Here we have two blocks on a table. This block has a mass of 10 kilograms. This block has a mass of 5 kilograms. We've got two resistances. Okay, so it's going to be friction in this case. 200 newtons acting on the first block, 100 newtons acting on the second block. And there's also a driving force of 400 newtons acting over here. So what unknowns do we have? Well, we don't know what the acceleration is of the system. What we do know is with all of these questions, they'll be accelerating at the same rate. In other words, the thing that's connecting the two things is inextensible. So if this moves by a certain amount, that has to move by the same amount. So they are completely joined together. And we also have this unknown tension force, T, acting in the connection. So in this case, it's probably a piece of string or something. Okay, so how do we calculate A? Well, we just apply F equals ma. And because we're not interested in the internal tension force, then what we can do is we can treat this whole thing as one single object. So we've got a 5 kilogram mass, a 10 kilogram mass. So the system in total has a mass of 15 kilograms. It's got a 400 Newton force to the right, and it's got a 300 Newton force to the left, and it's got our acceleration acting to the right. And we just apply F equals ma to that. So I'm going to resolve this to the right, which essentially says 400 minus 300 is going to equal the mass times the acceleration. And that gives us that the acceleration is 100 over 15. We can divide top and bottom by 5, so that's 20 thirds. So it's about 6.7. 6.7-ish. Okay. And that's acceleration, so that'll be meters per second squared. And for first year, this will be very much constant. Okay, it'll all be constant. It'll all be nice and simple. The forces will be constant. The acceleration will be constant. There's nothing tricky going on here. It is just applying F equals ma and finding the value of the constant. Okay, so that's the acceleration. How do we calculate the tension here? Well, to do that, you need to either consider the left box or the right box. So the tension force is internal to the system. So if you apply it to the system, you'll get a T to the right and a T to the left. They cancel out, no use. You need to apply it to either the left box or the right box, doesn't matter which. And in fact, what I'd recommend is perhaps you just apply it to both as a check. So if I just consider the 5 kilogram box, then all the forces acting on the right, well, that's only the tension. And the force acting on the left, well, that's only the 100 newtons. Okay, this 200 newtons doesn't affect that box because that's only affecting the 10 kilogram box. The 400 newtons is acting on the 10 kilogram box. So it is just T and 100. And we know that the acceleration is 20 thirds because we've just calculated that in the previous part of the question. So now if we apply F equals ma to that by resolving to the right, we will get t minus 100 equals the mass, which is 5, times the acceleration, which is 20 thirds. So that's 100 thirds. Add the 100 to that, I'll get t. Therefore, t is equal to 400 thirds. And that'll be in newtons, and that's the answer. We can check that if you choose to. You don't have to. But in an exam setting, it is worth checking where you can. And I would just consider the second box. So 10 kilograms. Forces to the right on this box, we've got a 400 Newton force. Forces to the left, we've got this tension force, which I'm going to recalculate and hope I get the same number. And we've also got the resistive force of 200 newtons. And I know the acceleration is 20 thirds. And just apply F equals ma. So resolving to the right, I will get 400 minus 200 minus t equals the mass times the acceleration. So I get then that t, bring that across to this side, 400 minus 200 is 200, minus 200 thirds, well that's 600 thirds, minus 200 thirds is 400 thirds, which is exactly what I got here. So because that agrees, you can be rest assured that you have got full marks on that question. Okay, so that's a simple example of connected particles. A more complicated example then, example number 2. So we have a car of mass 1,000 kilograms. It's traveling along a straight horizontal road. Again, it'll all be horizontal in first year, so it's nice and straightforward. Gravity doesn't have an effect, at least a trigonometric effect. But I calculate the acceleration of the car when a resultant force of 2,000 newtons acts on it in the direction of its motion. So this is just a direct application of F equals ma. So we've got a resultant force of 2,000, and it's got a mass of 1,000. Oops, only 3 zeros, there we go. And we need to calculate the acceleration. So F equals ma, so the resultant force is 2,000. That's going to equal the mass times our unknown acceleration. That tells us that the acceleration is 2 meters per second per second. There we go, that's the answer to part I. Okay, so just using F equals ma, not even using connected particles theory here. Okay, part 2. How long does it take to increase its speed from 5 meters per second to 12 meters per second? Well, we can see the acceleration is constant. You'd expect that in these types of questions. So we can use SUVAT. So S, U, V, A, and T. S, I don't know what it is. I don't actually care either. So I just put a cross there. U, well, it's starting at 5 meters per second. It finishes at 12.5 meters per second. I know the acceleration is 2 seconds. And T is what I'm trying to find. So I want a SUVAT equation that doesn't contain an S. You can check the formula book. That is V equals U plus AT. And just plug in the values. So 12.5 is going to equal 5 plus 2t. And that gives that t is 7.5 over 2, which is 3.75. And that would be in seconds because the acceleration is in meters per second, and that's because the tension is in newtons and the mass is in kilograms. And we're also given that the velocities are in meters per second. So all the units are SI units, so therefore time is SI unit. 3.75 seconds is the answer. Okay, again, that's not a connected particle bit. That's just using SUVAT on an F equals ma question. However, now we have a trailer that's being attached to the car. And here's our connected particle situation. The car has a driving force of 2,000 newtons and it has a resistance to motion of 600 newtons. And the trailer has a mass of 800 kilograms. The tow bar connecting the car and the trailer is light and horizontal. And the car and the trailer are accelerating at 0.7 meters per second. Calculate the resistance to motion of the trailer. Okay, so with these questions, it is always worth drawing a diagram. The diagram doesn't need to be anything fancy. I tend to do either rectangles or circles. So we've got the car with a mass of 1,000 kilograms. We've got the trailer with a mass of 800 kilograms. We've told the driving force of the car is 2,000. We're told there's a resistance of the car. Are we? Yes, there it is. And a resistance of motion of 600. So there's a resistance of motion there, 600. We don't know the resistance to motion of the trailer, so I'm just going to call that R. Okay, that's what I'm trying to find. And we don't know T, we don't know the tension. I'm going to do this in purple. So there's my internal force in the coupling between, or the tow bar, between the car and the trailer. Okay, so this part 3, calculate the resistance to motion of the trailer. I don't care about T, so I'm just going to treat the whole thing as one system. So if I resolve to the right, I get that the 2000, which is all the forces to the right, minus 600 minus R, which is all the forces to the left. That equals the mass, which is 1800. That's the mass of the car and trailer, times the acceleration, which we're told is 0.7. And that is a nice linear equation in R. You should definitely get your calculator out for to solve. So R is 2000 minus 600 minus 1800 times 0.7. And that is 140 newtons. Okay, so there's the resistance of the trailer, 140 newtons. Calculate the force in the tow bar. So this is now looking at the internal force, which means I either need to look at the trailer or the car. Let's just look at just the trailer. So resolving horizontally on the trailer, I'll get T minus R, which is 140. That equals the mass, 800, times acceleration, which is 0.7. That is a linear equation in T, which I can solve. So this time I'm going to get 800 times 0.7 and then add the 140, and that comes to 700 newtons. And we should check that. So if I resolve to the right just on the car, I'll get 2000 minus 600 minus the tension equals the mass times acceleration. And if I solve that, I will get 2000 minus 600 minus 1000 times 0.7. And that gives me that T is 700 as well. So in both those calculations I used, in the top calculation I used that R is 140. But the fact that both of these have come out to be the same not only confirms that the T is 700, but also confirms that the R is 140. So you can move on from parts 3 and 4 knowing you've got full marks. That was a check. Okay, you didn't need to do that. That was the calculation, and I used the trailer to do that. In all honesty, just looking at this in hindsight, it should have really been better for me to use the car here to calculate it, because if I got this answer wrong for whatever reason, I would have got a follow-through error. Whereas if I used the car, then I didn't use that value, so I wouldn't have lost a second mark for the same error. But if you check it, it doesn't actually matter. Okay, and finally, there's one last part to this question. The driving force is removed and a braking force of 610 newtons is applied to the car, and all resistances are as before. Calculate the force in the tow bar, stating whether it is intentional thrust. Okay, so again, I'm just going to draw a little diagram here. So I've got the trailer, which is 800. I've got the car, which is 1000. I've got the tow bar, which I'm going to assume for now has a tension. And if the tension is not correct, then T will be negative. It's got a resistance to motion of 600, and it's also now got a braking force of 610. So that's now 1,210 to the left, and the resistance of the trailer is still 140. There's now no driving force. I don't know what A is either. The acceleration has changed because the forces have changed. Okay, so resolving to the right, what I'm going to do is, because I'm just interested in the tension force, I'm actually going to apply F equals ma to the whole system and to either the car or the trailer, and then eliminate A from the system of equations. So if I resolve to the right, on the whole system, I will get minus 1,350, which is all the forces to the left, okay, no forces to the right. That's going to equal the mass times our unknown acceleration. And also, if I resolve to the right on either the car or the trailer, then I can get t. So I'm going to do that on the trailer. So t minus 140, that's going to equal the mass times the acceleration, which I don't know what it is yet. Okay, the top equation is just an equation with a in it. So if I do minus 1,350 divided by 1,800, that gives me that a is minus 3/4. And then I can use that in the bottom equation to calculate t. So I'll get 800 times minus 3/4 plus 140, and that will give me minus 460. Okay, so that's the tension, but that's come out to be negative. So to answer the question, the force is equal to 460 newtons, and that is in thrust or compression. And thrust or compression is defined as a negative tension. Okay, so rather than the tow bar pulling the trailer, the tow bar is actually pushing against the trailer to slow it down faster than it would have been had it just been rolling. Okay. Yes, that's an example question. Hopefully you'll find this video useful, and next video we'll be looking at pulleys. Thanks for watching.